Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we are strapping in for a true deep dive into mechanical engineering. Our mission really is to zoom in on those brilliant, often hidden mechanisms, the ones that manage extreme force, ensure absolute precision, or, enable technologies that quite literally reach for the stars. We've pulled from a huge stack of sources, covering everything from basic drives to uh, NASA robotics.
And if you think about it, what we're really exploring is this fundamental tension that every single engineer faces.
Mm.
How do you get maximum rigidity or this really complex, smooth movement while at the same time fighting friction, minimizing wear, and of course keeping everything as small and light as possible?
Right.
We're looking at some really clever solutions for motion, for control, and assembly across just vastly different scales.
Okay, let's unpack that. Let's start with mechanisms designed to solve scale and structural integrity. Think about something that seems deceptively simple: springs and booms.
Like a tape measure.
Exactly like a tape measure. Or an old coil antenna. You know the problem. They extend super easily, but when they're fully out, they have almost no torsional or flexural rigidity.
You just flop everywhere.
They just flop. And if you're engineering, say, a long boom for a spacecraft, floppy is just, well,
It's not an option.
not at all. That floppy mode means instability, vibration. It could mean catastrophic failure in an environment where precision is everything.
So the early solutions had to get clever with geometry to solve this. We see approaches like de Havilland stem and Hunter Springs helix.
Right, which both used overlapping material.
Yeah, that overlap creates a stronger sort of double-walled structure.
But the real ingenuity kicks in when you move beyond just simple overlapping. Take a design like Melpar's Tube-O-Matic. There, the strip of metal that unrolls isn't just overlapping. It actually has interlocking tabs and slots.
Ah, so they physically lock together.
Precisely. When it's fully extended, those tabs lock, and it forms a truly robust, self-supporting tube. And here's where it gets really interesting for anyone who cares about application. Melpar also added a row of perforations right down the middle of that strip.
And those weren't just for looks.
Not at all. They were a control mechanism.
Exactly. Those perforations help to accurately control the length during extension or contraction. It acts almost like a ratchet or a counter.
Which made it much more attractive as a precision positioning device, not just a structural element.
Right, for things like scanning systems or deploying a delicate sensor.
And all of that structural integrity depends on the material holding its shape, which brings us to the genesis of pre-stressing metal. This is all about material memory.
It is. I mean, John J. Park at NASA Goddard was facing a situation where the technical papers just didn't exist. He needed a metal strip to hold a tight curl after being flattened and extended over and over again.
And nobody had written the manual for that yet.
No, he had to start completely from scratch.
So he basically pioneered the method. He figured out how to give these metal strips a new memory.
He did. He used strips of beryllium copper alloy, which is already a fascinating choice, 2 inches wide and only 0.02 of an inch thick.
And the method itself was, well, it was elegant in its simplicity.
Yeah, it really was. He rolled the strips lengthwise into a glass tube, about 0.65 inches in diameter, and then he just heated it in a furnace under very controlled conditions.
And he found that the heat treatment was everything.
Everything. The longer or hotter the treatment, the tighter and more permanent the curl.
So he could basically dial in the geometry at the atomic level. I think one example was 920 degrees Fahrenheit for 5 minutes.
And that resulted in a tube that perfectly maintained that 0.65-inch diameter.
Yeah.
That's the kind of precision that makes long-life space systems possible.
And that idea of mastering controlled deformation is a perfect pivot to talk about motion where friction is the #1 enemy. Let's talk about flexures.
Flexures, or flexible suspensions, they're a really counterintuitive solution.
Because they don't roll or slide at all, do they?
Not at all. They completely avoid the mechanics of rolling or sliding bearings because they just flex. They act like a spring that allows for rotation.
And that simplicity translates into massive reliability.
But absolutely. No rubbing parts means no wear. They don't need complicated lubrication, and critically, they aren't really subject to backlash.
That little bit of slop or lost motion you get when a gear reverses direction.
Exactly. And for high-precision systems, that's a huge deal.
And they do some unbelievably heavy-duty work. I'm thinking of the Apollo Applications Program. A single flexure pivot, barely 2 inches high, was holding a 5,000-pound telescope.
And keeping it pointed at the sun with, and this is a quote, unprecedented accuracy.
That's frictionless precision supporting extreme weight.
And it works on Earth, too. They're used in submarine gimbal mounts, satellite safety shutters, even high-precision balance scales. They replace the old knife edges that get gunked up with dirt and dust.
That need for robustness doesn't stop at pivots. It's critical in safety and control mechanisms, which brings us to rotary override spring mechanisms.
These are just brilliant for motion control. They introduce a kind of controlled segmentation.
What do you mean by that?
Well, they're designed to transmit only a small, specific part of a total rotation to an output lever. Or they can be used to strictly limit the travel of that lever, even if the input is still spinning.
So if the input shaft spins a full 360 degrees, the output might only move for, say, 40 degrees of that, and the spring handles the rest.
Precisely. We've seen designs capable of segmenting 270 degrees of movement and others limited to just about 40. The beauty of it is the principle scales up. You can use it in heavy-duty machinery just by strengthening the components. It's all about controlled, repeatable yielding under a load.
And if we're talking about controlled yielding, monitoring shear force is critical, especially with high-tension cables. Thomas Grubbs at NASA came up with this marvelously simple lever system for that.
It really is mechanical elegance at its best.
Yeah.
You have two pulleys on a single pivoted lever. The cable you're monitoring runs between them.
Okay.
As the cable tension changes, the lever pivots up or down just a tiny bit.
And that tiny movement is what you measure.
That's it. The pivoting motion pulls on a little flat metal tongue.
And that tongue is what translates the mechanical action into a signal.
Exactly. A strain gauge is cemented right onto that metal tongue. The force from the lever directly strains the gauge, which gives you a continuous, immediate electrical reading of the tension. No complex gears, no linkages, just a simple lever. It's incredibly reliable.
That is elegant. But the complexity really jumps when we talk about integrated safety systems, like a crane overload warning device. That has to process two different inputs at the same time.
It's basically an early analog safety computer. It's dealing with two critical linked factors.
First is the boom angle.
Right. A low angle creates a much greater overturning torque. But then there's the compression load, or the cable tension, which is often greatest at high boom angles when you're pulling straight up.
And the system has to know which combination is the dangerous one.
It always has to warn of the danger, no matter the cause.
So how does a purely mechanical and hydraulic system do that? How does it integrate load and angle at the same time?
Okay, so first, a tension-to-pressure transducer converts the load into proportional hydraulic pressure. That pressure feeds a Borden tube pointer.
Which is basically a coiled tube that tries to straighten out under pressure.
Exactly. And the pointer on the end of it carries a small magnet. So the position of that magnet tells you the load.
Okay, that's the load. What about the angle?
The boom angle is monitored by a cam, which is linked directly to the boom itself. And this cam positions a series of magnetic reed switches along the path of that pointer.
I see where this is going.
The alert only triggers if the load component gets close enough to one of the switches, the angle component. The cam is shaped so that at a dangerous angle, it moves the switches closer to the magnet's starting position.
So it takes less load to trigger the alarm.
That's it. It's fail-safe. It flags an unsafe lift whether the danger comes from a heavy load alone or a lighter load at a dangerously extended angle. Truly ingenious non-digital integration.
Okay, moving from force management to motion transformation, let's talk about gearing. Specifically, gearing designed for high power redundancy and high ratio efficiency.
A great place to start is the twin-motor planetary gear drive, a brilliant solution for safety in things like hoists and cranes.
The genius here is providing redundancy without really sacrificing performance, right?
It's mechanical synergy at its best. You have two motors of equal rating. One drives the ring gear, the other drives the sun gear. If both run at the same speed, the output, which is the cage holding the planet gears, revolves at that speed.
But the safety factor kicks in if one motor fails.
Exactly. If one motor fails completely, the cage still revolves, but now at exactly half its original speed.
And critically.
Critically, the unit maintains its full lifting capacity. The working motor is still providing full torque. It's a beautifully reliable system that also gives you two working speeds without complex shifting.
Okay, so contrast that robust safety-first design with something like the harmonic drive reducer, which is all about getting massive speed ratios in a tiny space.
The harmonic drive is mechanically complex. It actually uses elastic mechanics. You have three components: a wave generator, a flexible spline, the flex spline, and a circular spline.
And the ratio comes from the wave generator intentionally distorting that flex spline.
Right. It forces the teeth of the flex spline to mesh with the fixed circular spline. but only at 2 points, 180 degrees apart.
Mm.
And because the flex spline has a slightly different number of teeth, one full revolution of that wave generator causes only a tiny, tiny rotation in the output.
You get huge speed reductions, hundreds to one.
And a very small volume.
Yeah.
But there is a key mechanical drawback you have to manage, which is windup.
You mean a torsional spring rate?
Yes. As the torsional load increases, like in a robotic joint, the flex spline itself has to flex slightly. This can cause adjacent teeth to engage a little bit before they're supposed to. If you need absolute zero backlash precision, that windup is a critical factor you have to design around.
While those drives manage big rotational loads, the IBM linear micron positioner takes us to the total opposite extreme. Micro-precision linear control with simple mechanics.
This thing is incredible. A low-cost mechanism that achieved fine focus control for a camera lens down to 10 millionths of an inch. Wow. And it uses a very simple differential circumference principle. Imagine two concentric cylinders with slightly different diameters, connected by flexible shim stock bands.
So when you rotate the inner cylinder, the difference in circumference between the two dictates the tiny linear travel of the output.
That's all it is. And if the diameters are very close, the reduction ratio is massive, theoretically capable of 10,000 to 1.
You see that same need for hyper-precision in something like the NASA triple-gang lead screw mechanism.
Right, which was designed for tuning microwave resonant cavities.
Where the challenge wasn't just tiny movement, it was maintaining absolute parallelism. If that moving plate tilts even slightly, the whole cavity is ruined.
The solution was pure mechanical synchronization. A large central gear simultaneously drives 3 separate, perfectly synced lead screws, one at each corner. This guarantees the movable plate never tilts.
That's a great transition into our final section, where mechanisms get really tiny, autonomous, and use some pretty advanced material science.
We have to first acknowledge the role of computer-aided design, or CAD, the shift from 2D CAD, which was really just automated drafting,
To full 3D solid modeling. That's where the design intelligence really lives.
It is. 3D modeling gives you incredible visual fidelity, sure, but more importantly, it consolidates all the information for faster flaw detection, stress analysis. You build complex assemblies using Boolean operations union, subtraction, intersection on simple shapes like prisms and spheres. It's digital construction.
But the real revolution in tiny machines is microelectromechanical systems.
MEMS, machines fabricated directly onto a silicon chip.
So silicon isn't just for electronics anymore, it's a structural material.
And it's an almost perfect mechanical material. It lacks mechanical hysteresis, which means it doesn't lose energy or change shape permanently when you bend it. Its yield strength is greater than stainless steel, and its strength-to-weight ratio is better than aluminum.
And the manufacturing is basically just advanced microcircuitry fabrication. You're using lithography to build gears and springs.
Exactly. Processes like Summit V, a 5-level micromachining process, let you build incredibly intricate things like microtransmissions right on the chip.
And how do you power something that small?
One common way is a comb drive, which uses electrostatic force.
So it relies on the attractive force generated between those little interdigitated fingers in the comb structure.
Right, and the force is governed by the energy stored equation, calculated as E equals CV squared divided by 2, where C is capacitance and V is voltage. You need a huge number of those little fingers to generate a useful amount of force.
And finally, let's go back to NASA for robotic mechanisms designed for hostile environments where a human hand just can't go. The probe and socket fastener.
This was designed to be robot-operated, so it had to be foolproof. Self-aligning.
To prevent it from binding during insertion.
Right. The socket has these tapered grooves and ridges that mesh perfectly with the probe, forcing it into alignment. The whole thing uses spring-loaded lock pins that are retracted by an actuator, so the robot can just push, click, and it's mated securely.
And for ultra-fine adjustments in huge structures, there's the inchworm actuator.
Proposed as an active truss member to counteract subtle vibrations or even change the configuration of a whole truss.
And it uses piezoelectric actuators.
3 of them, along with Belleville washers. Piezoelectric devices expand or contract with extreme accuracy when you apply electricity. The clever bit is the Belleville washers, which are cone-shaped springs. They apply constant preload.
Which is key, because it means the overall length is maintained without constant power. It locks its position mechanically.
It does. And the precision is staggering. A stroke accuracy of 0.0001 centimeters, you get micro-level control over a macro-level structure.
We've really traveled today, from thermalset copper booms to purely mechanical analog safety computers, and then all the way down to machines built on silicon.
It really emphasizes how engineers solve problems. Sometimes it's by leveraging simple, elegant forces like springs and levers, and other times by exploiting cutting-edge material science to get precision at any scale you can imagine.
The core principles really do stay the same even as the scale shrinks.
They do.
We saw how James Daniels' mechanical linkage could produce near-perfect straight-line motion without any guideways, just through link proportions and pivot placement. So here's a thought for you to mull over. In a world moving so fast toward MEMS and fully digital control, what classic, purely mechanical mechanism do you think will remain irreplaceable just because of its inherent elegance and robustness? That's it for today, Design Junkies. If you're getting something out of this, follow the podcast and leave a review. It helps the whole family grow, learn, and build better together.